This lesson is going to go through talking about how can we define congruence using rigid motion. So back in Unit 5, we talked a lot about, Unit 5 in coordinate algebra, we talked a lot about transformations that we called isometries. And those included translations. If you recall, translations were the slides. They moved left and right or up and down. We also talked about reflections, reflecting over the x-axis, reflecting over the y-axis and such, and then also rotations. All of those were called isometries because they maintained the shape and size. They were rigid motions. So we're going to use those rigid motions to determine whether two figures are congruent. So if you recall, congruent figures are going to be ones that are identical in size and shape, but they don't necessarily have to have the same orientation. So notice if we could take this first figure and move it or translate it or transform it using those rigid transformations, we can do that in order to map it onto the other one or to show that they are congruent. So when you look at this, it asks if the following pairs of figures are congruent. So if I look at these, it looks as though these are congruent. B and C both look as though they include a dilation, so that wouldn't be congruent. And D, I think, is sort of arguable, but to me it appears as though they are congruent. How do I know whether or not they're congruent? Well, again, if I can move one so that it's on top of the other and it's the exact same shape and size, then they would be congruent. When I look at these, which two of these are congruent? It looks like B and E are congruent. If you look at the shapes, they would be the same. And then the second one, the figures that are congruent, and actually it's not just two, it's I believe it's more than two. I believe it's A, C, and D that are all congruent. And if you look again, if I take this one and I reflect it, it would lay on top of this one and show that they are congruent. Now when it's not on a coordinate plane, it's a little bit harder to tell when we look at these, but we're going to be looking mostly on the coordinate plane. Alright, so for this one it gives me two quadrilaterals and it asks me to figure out certain measures, and it tells me that they are congruent. One thing to note is the letter of the order of the letters. So if I have E, F, G, H, and it's telling me that that is congruent to A, B, C, D, then the order of the letters is important. E and F are a side length right here, and those are going to be congruent to A and B. That's the AB, that's my corresponding side. So this side and this side are corresponding sides because of the order of the letters. So EF, when it asks me what the length of EF is, it would be the same length as AB because EF and AB are both the first two letters in my when I named it. So EF would equal 10 centimeters. Okay. It asked me for the measure of angle FGH. FGH is this angle right here. Well, I have to figure out what angle it corresponds to in this figure over here. So I need to figure out that, and I'm going to use these letters right here. When I look at these, I'm going to label these side lengths over here just to help orient me a little bit better. We said that EF and AB were congruent. GH and CD are also congruent. So CD is right here, it's 8. And GH is right here, it is also 8. Alright, and then when I look at these two, I can look at the middle two letters, FG and BC. Those are congruent, so BC and FG, that one's 7.8. And then I can just say, okay, well then this one must be 12. Alright, so when I look at my figure now, it asks me for the measure of angle FGH. That's this angle between the 8 and the 7.8 sides. So when I look at this one, I've got between the 8 and the 7.8 sides, which would be this angle right here of 98. So angle FGH has to also be 98 degrees. The perimeter of EFGH would be the same as if I added up all of this, all of these sides. It's going to be the same for both figures. So that gives me 2037.8 for my perimeter. So if I'm going to use transformations to define congruence, again, I'm only going to be able to use those rigid transformations, those isometries that we talked about at the very beginning. So we can rotate in order to get it to fit on top of each other. So notice it says we can translate it by rotating it. Here we can reflect and then translate. So we can use a combination of transformations in order to do that. Remember that two figures are going to be congruent if one figure lies exactly on top of another after a combination of translations, rotations, and reflections. But this does not include dilations. So only translations, rotations, and reflections. So we're going to use that idea right here. There are many answers that you could give, but we're trying to get transform A onto B by showing that show that they're congruent by transforming A onto B. So again, there's many ways that you could do this. One would be to reflect it over the x-axis. So reflect over, remember this is y equals 0. If I reflect it over that, it's going to look like this. Oops, my bad. Try that again. There we go. It's going to look like that. And then I still have to move it down 1 and to the right 1, 2, 3, 4, 5. So remember that we can write like this. To the right 5 would look like this, and down 1 like that. But again, there's many different combinations that you could use. That's the same, that I've written here. But you could, you could have reflected over a different line in order to get that, where you need it to go. You could reflect it over the y-axis and the x-axis, and then, move it down. So whatever, makes the most sense to you. All right, again, we're going to show that they are congruent by describing the combination of transformations that fit F onto G, or excuse me, H, J, K onto D, F, G. So notice this one, it looks as though we're going to need to use a rotation. So just as a reminder, let's talk about those rotation rules. For 90 degrees counterclockwise, which is the same as 270 degrees clockwise, if you recall. The rule for that is to take my point and to switch the order and make that first one negative. For 90 degrees clockwise, which is the same as 270 counter, I'm going to take my point and I'm going to switch the order but make the second one negative. Remember, 180 degrees does not matter clockwise or counterclockwise. I'm going to take my point and I'm not going to switch the order, but I'm just going to make both of them the opposite. Remember, this doesn't necessarily mean that the coordinate will be negative, it just means that it's the opposite sign of what it was before. So if you don't remember that from Unit 5 in coordinate algebra, you may want to write those down in your notes. Alright, so when I look at this one again, I'm going to decide what needs to happen to get this figure on the left on top of this figure on the right. So it looks like we're going to have to use a rotation clockwise. If we do that, if I take a point, let's see, right here I want H to map right here onto D. So if I rotate that 90 degrees, H has the coordinate -1, +3. So that means if I rotate it 90 degrees clockwise, I'm going to switch the order, which would be 3, -1, but then I'm going to make this second one the opposite side. So it's going to be 3, +1. So if I do that, that puts this point right here instead of right here, which means I'm going to have to rotate it and then translate it to the left one. So I've got to rotate 90 degrees clockwise. and then shift it to the left one, which would look like this. All right? So by doing those two rigid transformations, I can show that they are congruent. I'm going to show that ABC and RST are congruent by describing the combinations of transformations. Again, in this case, it looks as though I need to reflect it. If I reflect it over the y-axis, so if I reflect over the y-axis, which is x equals 0, right, then that would put me, 1, 2, 3, 1, 2, 3, it would put me here. And then I need to move it down 1, 2, 3, 1, 2, 3, 4, 5. So I'm going to move it down 5, which would look like this. Okay? To determine if these two are congruent by identifying the transformations, in this case they don't give us an x and y axis or an origin, so in this case we're just going to be more general. We can count the lengths of the sides, 3 and 5 and 3 and 5, and note that they are the same, so they have to be congruent. And in this case, we are going to just look at a reflection and a translation. It looks as though we could reflect it over this line right here, oops, and then translate it to the right in order to get it in the right, the letters in the right orientation and everything in the right spot. Again, if I'm going to determine if these two figures are congruent, if I look at this, it looks as though they are not the same size. And remember, that would show that it's not congruent. This would actually be a dilation. And later on, we'll talk about similarity and similar figures using dilations. But right now, we're just focusing on congruent figures. The last one, again, is to determine if they're congruent. It looks as though we're going to have to take our original and we're going to have to rotate it. And it looks like if we rotate it counterclockwise, that would work the best. So again, because there's no x or y axis or no origin marked on here, I would be okay with you just saying a counterclockwise rotation. And it's likely that after that counterclockwise rotation, you may also need a translation as well. So again, if I can take a figure and use these rigid motions, these translations, these rotations, and these reflections in order to map a figure onto a different figure and they fit perfectly, then I can prove that those two figures are congruent.